Hello, students. Let's talk about the greatest common divisor of two numbers. Okay. So how do we find the GCD of two numbers? Well, GCD stands for greatest common divisor, and this is one of the best named things in mathematics. I mean, it tells you what the greatest common divisor is, because all you have to do is say it out loud. It's a divisor. It's a common divisor, so the divisor has to divide both of them, right? It's common to both numbers. But not only that, it's the greatest of all the common divisors. So this exactly tells me what it is. So what's one way that I could do this? Well, there's many ways that we could actually do this in Python if we wanted to write code to find the GCD. Let's think about what some of them are. So let's do just a quick example of some GCDs. To get used to things. So let's say we want the GCD of 48 and 20. So this is a number that divides 48 and divides 20. Now, if you divide two numbers, then you divide their sum and you divide their difference, right? If any number that goes into 48 and 20 is going to have to go into 48 minus 20 because it goes into both of them evenly. So this is the same thing as this 48 minus 20. And 20. In fact, I could subtract off 20 twice. And this is going to be the same as that, which is what? Well, this is like the GCD of 20 and 8. Okay? Well, I could do that again. What I could do is I could say, okay, I want the GCD of 20 and 8. What could I do? Well, it's the same as 20 minus 8 and 8, which is the same as the GCD of 20 minus 8 twice. You see what I did there? I wrote what 8 times 2 was, but I want to keep it as 8 times 2. I don't want to write the 16 out. Okay, and 8. Okay, so what's 20 minus 16? That's the GCD of 8 and 4. Now you might say we don't need to go through all this work. You could possibly figure this out on your own. But let's just keep going. Well, this would be the GCD of 8 minus 4 times 2 and 4, which is the GCD of, well, it's 4 and 0. And then once one of the numbers is 0, we know what the GCD is because every number divides 0. Remember, 0 doesn't divide anything, but everything divides 0. That's the direction you have to keep in mind. Okay, so I know if I get the smaller number to be 0, I could just take the bigger number, and that's going to be the GCD, right? Because 4 divides 0 and 4 divides 4. Otherwise, what I could do is I could actually, what's going on here? Well, I'm dividing by 20 basically and taking, what is this? The remainder. Here I'm dividing by 8, and what is this? This is the remainder. So the GCD of A and B is actually going to be equal to the GCD of B and A mod B, the remainder when I divide A by B. And we'll try to keep the bigger one on the left. We'll see how that works. Okay, so let's write some code. We might have more than one GCD attempt, so I'll put a GCD1 there. And now let's try to write this. So what do we want it to return? Well, we want it to return A if B is 0, right? Just like we had right here. If B was 0, we just return the bigger number. We won't worry about what happens if we get the numbers out of order yet. Let's just get this down. Else, not return because we're already returning. This is the ternary operator here. So otherwise what we're going to do is we're going to return GCD of 1 of B, A mod B. Okay. Now, let's say I ask what the GCD1 is of 48 and 20, and you'll see it very nicely gives me 4. This sort of computation is called the Euclidean algorithm. It's a very fast way of finding GCDs because it requires just one remainder, and then we replace, and it can shrink big numbers down to small numbers very, very quickly. So this is a very efficient way of doing it. But what happens if I put the big number on the right? I mean, we could always tell the user not to put the big number on the right, right? But, that still worked. Why is it? Why is it working? Well, it turns out that if you put the big number on the right, remember, the A and the B were also swapping. So because I wrote A, B, and B, A mod B over here, that's actually going to make this work. If I had written A mod B on the left, then I might run into some trouble based on what inputs I give it. But there's no trouble to be found. This is a nice one-line way of finding the GCD. Okay, let's try just from the definition of GCD. Let's say I didn't know Euclid's algorithm here. So we don't want to go all the way back to ancient Greece. So let's find the divisors of A and B. So new way, definition, GCD2 of A and B. So I could find the divisors of A. So I can make the list of all I for I in range 1, 2, and including A. I want to include the ones where if I divide, I get 0 as the remainder. I want things that go in evenly. And I'll be lazy here. My laziness is punished. But hopefully that is not lined up nicely here. And what do I want? I want the maximum thing in common. So I want the maximum, and you know, I don't even need lists. These can be sets. I can make my life even easier here. I want the maximum thing in common. So what's the word for the things that are in common in both sets? Well, that's the intersection, and we know how to get that, right? So I could take the intersection of the divisors of A and the divisors of B, and I want the maximum of all of those things. So let's try that. So let's see if this works. GCD2 of 20 and 48. And yes, it works nicely. So what it's doing is it's getting all of the divisors of A and all of the divisors of B, taking the intersection and then taking the maximum of those. Okay. You might think that that's a little much, because why do we have to find both of them? What I could do is I could just look at the divisors of A once I have that, and then see which of those divide B. So let's try that. GCD3, A and B. So what I want is, let's say, I'm just going to start with a return here. So I'm going to take the set of all I for I in range 1A plus 1 if it divides A and B. B mod I equals 0. So basically, I'm going to go through all the possible divisors of A. I don't know whether A or B is larger. You know, maybe A is the larger one, maybe A is the smaller one. The other function worked for both. Why not this? And what I'm going to do is I'm going to quickly check through the divisors of A, but while I'm checking the divisors of A, I also check for divisibility by B, because I know I have to divide both of them anyway. So why compute these two things at once? I just run through once. And this is going to be a faster way of doing it. GCD3 of 20 and 48. Except I forgot to take the maximum. So let's do that, because I want the greatest common divisor. And there we go. Now I've gotten the greatest common divisor. And I don't even need this. It'll still work regardless. Okay. If I really wanted to optimize for speed, what I could do is I could figure out which is the smaller number and just run through the minimum. So like what I could do is if I had GCD of 4, I could let M be the minimum of A and B, built-in function minimum, and I could let M be the maximum of A and B. And now I could run through the minimum and check that it divides the minimum and the maximum of those two. And now it'll always be running through the smaller of the two numbers. Except I want to test out GCD4. This is really good if you have like something like really big like that.